In electrical engineering and control theory, a Bode plot (ʻboʊdi) is a graph of the frequency response of a system. It is usually a combination of a Bode magnitude plot, expressing the magnitude of the frequency response, and a Bode phase plot, expressing the phase shift. Both quantities are plotted against a horizontal axis proportional to the logarithm of frequency. Given that the decibel is itself a logarithmic scale, the Bode amplitude plot is log-log plot, whereas the Bode phase plot is a lin-log plot. As originally conceived by Bode in the 1930s, the plot is only an asymptotic approximation of the frequency response, using straight-line segments. However, with the advent of locus computing, it is often taken nowadays to mean the precise plot of the actual frequency response. Overview. Among his several important contributions to circuit theory and control theory, engineer Hendrik Wade Bode, while working at Bell Labs in the United States in the 1930s, devised a simple but accurate method for graphing gain and phase shift plots. These bear his name: Bode gain plot and Bode phase plot. Bode is pronounced ʻboʊdi, ʻboʊdi. Bode was faced with the problem of designing stable amplifiers with feedback for use in telephone networks. He developed the graphical design technique of the Bode plots to show the gain margin and phase margin required to maintain stability under variations in circuit characteristics caused during manufacture or during operation. The principles developed were applied to design problems of servo mechanisms and other feedback control systems. The Bode plot is an example of analysis in the frequency domain. Definition. The Bode plot for a linear, time-invariant system with transfer function consists of a magnitude plot and a phase plot. The Bode magnitude plot is the graph of the function of frequency. The axis of the magnitude plot is logarithmic and the magnitude is given in decibels, i.e., a value for the magnitude is plotted on the axis It. The Bode phase plot is the graph of the phase of the transfer function in degrees plotted logarithmically as a function of. Examples. High-pass filter. The one-pole high-pass RC filter has the transfer function, whereas the inverse of the cutoff frequency magnitude plot. To obtain the Bode magnitude plot, one calculates the magnitude of the transfer function along the imaginary axis. The last equality is obtained using the rules for complex numbers. On the Bode magnitude plot, decibels are used, and the plotted magnitude is phase plot. To obtain the Bode phase plot, one calculates. Care must be taken that the inverse tangent is set up to return degrees, not radians. The resulting Bode plot is shown in Figure 1. For low-pass filter, a passive low-pass RC filter has the following transfer function, where, again, is the inverse of the cutoff frequency. The corresponding Bode plot is shown in Figure 1. The magnitude and the phase of the transfer function are related. For minimum phase systems, there is a unique relationship between the magnitude and the phase, the Bode gain-phase relationship. If the transfer function is a rational function with real poles and zeros, then the Bode plot can be approximated with straight lines. These asymptotic approximations are called straight-line Bode plots or uncorrected Bode plots, and are useful because they can be drawn by hand, following a few simple rules. Simple plots can even be predicted without drawing them. The approximation can be taken further by correcting the value at each cutoff frequency. The plot is then called a corrected Bode plot. Frequency response and Bode plot. This section illustrates that a Bode plot is a visualization of the frequency response of a system. Consider a linear, time-invariant system with transfer function. Assume that the system is subject to a sinusoidal input with frequency that is applied persistently, i.e., from a time to a time. The response will be of the form i.e., also a sinusoidal signal with amplitude shifted in phase with respect to the input by a phase. In summary, subjected to an input with frequency, the system responds at the same frequency with an output that is amplified by a factor and phase shifted by. These quantities, thus, characterize the frequency response and are shown in the Bode plot. Rules for handmade Bode plot. For many practical problems, the detailed Bode plots can be approximated with straight-line segments that are asymptotes of the precise response. The effect of each of the terms of a multiple-element transfer function can be approximated by a set of straight lines on a Bode plot. This allows a graphical solution of the overall frequency response function. Before widespread availability of digital computers, graphical methods were extensively used to reduce the need for tedious calculation. A graphical solution could be used to identify feasible ranges of parameters for a new design. The premise of a Bode plot is that one can consider the log of a function in the form as a sum of the logs of its poles and zeros. This idea is used explicitly in the method for drawing phase diagrams. The method for drawing amplitude plots implicitly uses this idea, but since the log of the amplitude of each pole or zero always starts at zero and only has one asymptote change, the method can be simplified. Straight-line amplitude plot. Amplitude decibels is usually done using to define decibels, given a transfer function in the form where n are constants, and is the transfer function. At every value of s where, increase the slope of the line by per decade. At every value of s where, decrease the slope of the line by per decade. The initial value of the graph depends on the boundaries. The initial point is found by putting the initial angular frequency into the function and finding the initial slope of the function at the initial value depends on the number and order of zeros and poles that are at values below the initial value, and are found using the first two rules. To handle irreducible second-order polynomials can, in many cases, be approximated as. Note that zeros and poles happen when is equal to a certain or. This is because the function in question is the magnitude of, and since it is a complex function, thus at any place where there is a zero or pole involving the term, the magnitude of that term is. Corrected amplitude plot. To correct a straight-line amplitude plot, at every zero, put a point above the line. At every pole, put a point below the line. Draw a smooth curve through those points using the straight lines as asymptotes. Note that this correction method does not incorporate how to handle complex values of or. In the case of an irreducible polynomial, the best way to correct the plot is to actually calculate the magnitude of the transfer function at the pole or zero corresponding to the irreducible polynomial, and put that dot over or under the line at that pole or zero. Straight line phase plot. Given a transfer function in the same form as above, the idea is to draw separate plots for each pole and zero, then add him up. The actual phase curve is given by, to draw the phase plot for each pole and zero. If is positive, start line it. If is negative, start line it. If the sum of the number of unstable zeros and poles is odd, add 180 degrees to that basis. At every, increase the slope by degrees per decade, beginning 1 decade before. At every, decrease the slope by degrees per decade, beginning 1 decade before. Unstable poles and zeros or degrees. After plotting one line for each pole or zero, add the lines together to obtain the final phase plot. That is, the final phase plot is the superposition of each earlier phase plot. Example. To create a straight-line plot for the low-pass filter, introduced above, one considers the transfer function in terms of the angular frequency. The above equation is the normalized form of the transfer function. The Bode plot is shown in Figure 1 above, and construction of the straight-line approximation is discussed next. Magnitude plot. The magnitude of the transfer function above, given by the decibel gain expression, then plotted versus input frequency on a logarithmic scale, can be approximated by two lines, and it forms the asymptotic magnitude Bode plot of the transfer function. For angular frequencies below it is a horizontal line at 0 decibels, since at low frequencies the term is small and can be neglected, making the decibel gain equation above equal to 0. For angular frequencies above it is a line with a slope of -20 decibels per decade, since at high frequencies the term dominates and the decibel gain expression above simplifies to which is a straight line with a slope of per decade. These two lines meet at the corner frequency. From the plot, it can be seen that for frequencies well below the corner frequency, the circuit has an attenuation of 0 decibels. Corresponding to a unity passband gain, i.e., the amplitude of the filter output equals the amplitude of the input. Frequencies above the corner frequency are attenuated. The higher the frequency, the higher the attenuation. Phase plot. The phase Bode plot is obtained by plotting the phase angle of the transfer function given by versus, where and are the input and cutoff angular frequencies respectively. For input frequencies much lower than corner, the ratio is small and therefore the phase angle is close to 0. As the ratio increases, the absolute value of the phase increases and becomes -45 degrees when, as the ratio increases for input frequencies much greater than the corner frequency, the phase angle asymptotically approaches -90 degrees. The frequency scale for the phase plot is logarithmic. Normalized plot. The horizontal frequency axis, in both the magnitude and phase plots, can be replaced by the normalized frequency ratio. In such a case the plot is said to be normalized and units of the frequencies are no longer used, since all input frequencies are now expressed as multiples of the cutoff frequency. An example with pole and zero. Figures 2 to 5 further illustrate construction of Bode plots. This example with both a pole and a zero shows how to use superposition. To begin, the components are presented separately. Figure 2 shows a Bode magnitude plot for a zero and a low-pass pole, and compares the two with the Bode straight-line plots. The straight-line plots are horizontal up to the pole location and then drop at 20 decibels, decade. The second figure 3 does the same for the phase. The phase plots are horizontal up to a frequency factor of 10 below the pole location and then drop at 45 degrees, decade, until the frequency is 10 times higher than the pole location. The plots then are again horizontal at higher frequencies at a final, total phase change of 90 degrees. Figure 4 and Figure 5 show how superposition of a pole and zero plot is done. The Bode straight-line plots again are compared with the exact plots. The zero has been moved to higher frequency than the pole to make a more interesting example. Notice in Figure 4 that the 20 decibels, decade drop of the pole is arrested by the 20 decibels, decade rise of the zero, resulting in a horizontal magnitude plot for frequencies above the zero location. Notice in Figure 5 in the phase plot that the straight line approximation is pretty approximate in the region where both pole and zero affect the phase. Notice also in Figure 5 that the range of frequencies where the phase changes in the straight line plot is limited to frequencies of factor of 10, above and below the pole location, where the phase of the pole and the zero both are present. The straight-line phase plot is horizontal because the 45 degrees, decade drop of the pole is arrested by the overlapping 45 degrees, decade rise of the zero in the limited range of frequencies where both are active contributors to the phase. Example with pole and zero. Figure 2. Bode magnitude plot for zero and low-pass pole, curves labeled Bode, are the straight-line Bode plots. Figure 3. Bode phase plot for zero and low-pass pole, curves labeled Bode, are the straight-line Bode plots. Figure 4. Bode magnitude plot for pole-zero combination. The location of the zero is 10 times higher than in Figures 2 and 3. Curves labeled Bode are the straight-line Bode plots. Figure 5. Bode phase plot for pole-zero combination. The location of the zero is 10 times higher than in Figures 2 and 3. Curves labeled Bode are the straight-line Bode plots.